Thank you for today. Welcome to my YouTube channel. My name is Abdul Rashid Alao. I'm a chartered engineer and a member of Institution of Mechanical Engineering, United Kingdom, and also member of American Society of Mechanical Engineers. Today, I would like to talk about introduction to my research and teaching. My research is in the general area of materials, characterization, and fabrication. So, my research fosters the synthesis of multi-scale characterization of mechanical behavior for a variety of metals, materials for high temperature, energy, optical, extreme, and biomedical applications. It also focuses on the mechanics of advanced manufacturing processes such as additive manufacturing, precision engineering, and biomanufacturing. And you can see in the field of characterization, the microstructure of a material influences its mechanical properties, and its properties influences the processing that will be applied, such as machining, casting, shaping, extrusion, and so on. And the processing of the material will influence its performance, such as wear, fatigue, and so on and so forth. Um, I have a vast research skills. I'm well versed in nano and micro indentation techniques. And also I can use optical, scanning electron, scanning probe, atomic force microscope confidently. Also, I can also apply X-ray diffraction just to for phase content of material. Also, I can use the differential scanning calorimetry for the glass transition, melting point, and so on for thermal properties of material. I can also apply axial contact fatigue in order to understand the fatigue behavior of material. Then I can conduct tension, compression, bending, flexural fatigue, creep, and vibration tests. I can do some machining processes like milling, turning, and drilling, grinding using computer numerical control machine. Also, I can do all the above tests, tension, compression, bending, flexural fatigue on universal testing machine. Um, in the field of precision engineering, I have been able to apply conventional machining in order to get high quality surface, high surface quality on the silicon. You can see silicon represents a hard and brittle material, and because of its hardness, it features low machinability when machining done conventionally. However, there is a concept called ductile mode machining, which is a process whereby hard and brittle materials are machined in a ductile manner such that extensive micro cracking are minimized. So this one can apply, the concept can be applied to her to machine hard and brittle material in order to get high quality surface. So one of the processes you can use is known as precision grinding. You can also use precision or ultra precision diamond turning. You can also use precision micro milling. So what I used here was precision grinding, which is a finishing technique to produce complete with nanometric surface quality. So, but you have to I had to adapt the spindle of the numerical control milling machine that I used. I had to adapt it to a high speed grinding. That is, I had to attach a high speed jig grinder in order to improve or to enhance the spindle speed from 6,500 to 90,000 90,000 revolution per hour. Then by properly selecting the machining condition like depth of cut, feed rate, and spindle speed, I was able to generate a surface average surface roughness of 37 nanometer on general purpose numerical control instead of the special purpose grinding machine. And this surface condition meets ophthalmic condition, and the results were published in this journal. Then, talking about the mechanical behavior, at nanoscale, I was able to use nano indentation technique in order to get different deformation mechanism for different ceramic materials such as zirconia, lithium disilicate. Zirconia in presintered form and the one at sintered form. Now, for presintered zirconia, the plastic deformation that we reported it was a kink band. What is kink band? Kink band is a plastic buckling process. It is different from metallic plastic deformation in the sense that it generates a succession of, you can see, parallel dislocation band, okay, a succession of a pair of dislocation dislocation on parallel slip system. And then it was the first time this kind of plastic deformation was reported for pre-sintered zirconia. For the sintered zirconia, the plastic deformation reported was dislocation, initiation, and interaction. Then, by combining uh, strain rate model and pressure sensitive yielding model, I was able to extract or to develop another method to extract the yield strength of sintered zirconia in nanoindentation, which is different from the conventional method. Another thing that I discovered was that the deformation mechanism for lithium disilicate glass ceramics are shear bands and strain hardening. That is why it has got little or little when you compare the strength to that of zirconia. Then for all this, I was able to propose material removal mechanisms for sintered zirconia and lithium disilicate glass ceramics in order to avoid brittle fracture in CAD/CAM machining. Okay, then I went on to develop advanced mechanical behavior in order to know the dominant deformation mechanisms between elasticity and plasticity. So, because once the elastic deformation is dominant, it means the material will be more uh, prone to brittleness. But if the dominant deformation mechanism is plastic, the material can undergo um, higher ductility before its fracture. So it can absorb more energy before failure. So for presented zirconia, I discovered that it has got the highest ductility than it is the ductile is more ductile than sintered zirconia. For pressed lithium disilicate glass ceramics, this one is rated most ductile among the uh, lithium diglass lithium disilicate glass ceramics are manufactured by different processes. This one is pressed, heat and pressed. Another one is just sintered. The third one is pre-sintered lithium metasilicate glass ceramics. Then I developed for the first time the ductility of sintered zirconia reduced during strain hardening process, which is, I mean, similar to the strain hardening process uh, happening in ceramics. You can see these are all these pop-ins represent certain material characteristics, and I can see at low loading rate the deformation is very slow, where and then you can see, but at high loading rate you have a continuous or smooth deformation in the load distance uh, graph. Thank you.